Hello everyone and welcome to another webinar from World Electronics. My name is Silas Ton and I will moderate this webinar today. The topic of today is Safety by Design, X and Y, Interdifference, Suppression, Capacitors for Power Line Filters. Our speaker today is Jon. Hi Jon.
Hi.
Welcome. Cool to have you here. He is a hardware engineer in the field of capacitors. So now I will hand over to Jon and I wish you an exciting webinar.
Thank you, Silas, and let's get started. So, I will jump to the topics that we will discuss. Today we will speak in general about what it means, X and Y capacitors, why we need them as interference suppression capacitors, and I will explain why we use some technologies and not others. There is a main, because this is a safety aspect, there is a lot of regulation, especially I will mention different aspects inside the IEC 63814 standard. And then I will introduce some of our products and other resources that we have at World Electronic ISOs. So, first of all, X and Y capacitors and how we use them in mains voltage supply filters. So, what is a X capacitor? X capacitors are connected between phases or between phase and neutral in three-phase systems between each phase and in another. They can be connected in star or delta. And the main function of X capacitors is to suppress differential mode. So as you can see, differential mode is when differential mode noise is when we have noise current flowing in different directions in each phase. And the X capacitors, in this case, we have one before the common mode choke and one before and one after. The X capacitors provide a low impedance path for this current to flow. X capacitors also provide an important safety function because they are able to handle some surge voltage, and this is all defined in the standard, how much. And X capacitors are intended to fail open, but it's not a requirement. In general, if they fell short, normally there should be a fuse, so there is no damage to the equipment. Now, to compare, we have the Y capacitors. Y capacitors are connected between each phase and the protective earth, as you can see here. Now, the main function of Y capacitors is to suppress common mode noise. So common mode, it's called like this because it's noise that flows in the same direction in all phases. And as such, it cannot be suppressed by the X capacitors. Now, normally you will see this kind of filter, and the common mode choke is also playing a very important role in common mode suppression, as the name suggests. But the common mode choke is providing a high impedance path, so it's blocking the high impedance path for the current, so it's blocking the current, but the current has nowhere to go, as we could say, and the Y capacitors provide the low impedance path to earth to get rid of that noise. And this is also why normally we connect the Y capacitors in the side of the power supply or the converter, the switching side, because this is normally the source of the common mode noise. And in this example, we don't have Y capacitors in the mains side. Now, because Y capacitors are connected to protective earth, and normally this is also connected to the chassis, there are special safety requirements. The main, most important thing is that the capacitors are intended or designed to fail open, and this is difficult to prove, but there is normally a reinforced isolation structure inside, as we will see later, that provides a method to gain this. Because if they will fail short, we could come into the risk of connecting the live phase or live wires to the chassis, and we could put the operator into hazard. So it's very important that the Y capacitors have special safety requirements. Now, Y capacitors also are better suited in other applications when we want to, due to the reinforced isolation, when we want to connect capacitors between across the isolation barrier. But this is not what is the intended use in the IEC standard. One interesting aspect of Y capacitance is that we are not able to connect too much capacitance. Why is this? Because when we have AC voltage in any of our phases, we have AC current also flowing through the capacitor to earth, and this is called sometimes leakage to earth, which is not to be confused with the leakage as a DC isolation property of the capacitor. This is something different. It's a property of AC system, and this leakage current is normally monitored and then to detect current to ground failure, which normally could mean as also safety hazard. And we are not able to have a lot of leakage current because this will trip the safety systems. And there are very, very specific and strict regulations about how much the leakage current can be, depending on the application. For industrial or domestic devices, can be less and more. This is an example calculation that is provided from an application note, how we calculate the total Y capacitance and the total leakage current. These capacitors also have another interesting aspect. When we have its capacitance, it also means that we could, in theory, hold charge when we disconnect the power supply from the mains. And this could also put the operator into hazard. So there is also regulation in the equipment norms, like these are examples, but there are other, that we discharge quite fast the X capacitors. So we require this discharge or bleeding resistor. And how we calculate this is also another example from the application note, that we calculate the total X capacitance, and with this we can select the right resistor. One example of the typical requirement for discharge is that we have less than 60 volt after 1 second after we disconnected the power supply. This is one example, but there are other regulations. So what are the capacitors and capacitor technologies that are more suitable for X and Y capacitor placement? The most commonly used is metallized polypropylene film capacitors. So these capacitors are basically made starting with a foil, which is a thin polypropylene film, where we apply a very thin metallization, and this metallization is providing a conductive electrode. And you can imagine this is already looking like a plate capacitor from the basics. And we can stack these films, and we leave one exposed area without metallization here and here, and we can wind together these films, which have two separated electrodes. And when we have rolled it and pressed it, we can now spray some conductive material here on the sides. And as you can imagine, only one of the foils is connected here. And now we can weld the pins and put the roll inside of this plastic box. And this is how film capacitors are made, the boxed film capacitors. Finally, we fill the box with epoxy material or resin to protect the winding from the atmosphere. Now, the structure I showed you is the structure of a X2 or X. Normally, X2 film capacitor that doesn't have special structure for reinforced isolation. But for example, in our Y2 capacitors, you will find this kind of a structure where the electrodes that are connected to the pins are actually split in the middle, and then we have another inner electrode. So you can imagine this is looking more like two capacitors in series, and this is with this structure we can achieve higher voltage range and impulse voltage ruggedness, as well as as I mentioned, the double isolation and the protection against short circuit. Why do we use this metallized film structure? Well, we can get a lot of capacitance because the film is so thin and the metallization is so thin, so we can have more windings. But the main advantage is also that we have the so-called self-healing property. So if you apply voltage and somewhere in the dielectric film, in the isolation, there is some weak point, and this is the point where when we apply a voltage that is more than the breakdown voltage of this specific point, inrush current will happen in this point, and this is a high density energy episode. And in this point, in this spot, as you can imagine here, the metallization, the dielectric film will evaporate and make a hole, and then the metallization, because it's very thin and it's very sensitive, I could say, we can imagine that the whole area around the spot will also be vaporized, as you can see in this image, and this will allow us to have the capacitor working as it was, with let's say a better isolation, because now we repaired the point in the sense that we are not getting a short circuit, and the weak point is gone now. We have a better isolation for the whole capacitor, and the only problem is that we lost a little bit of electrode, but we have a functioning capacitor after the event, and it can be a high energy surge voltage event. Now, the other technology that is commonly used for X and Y capacitors is the ceramic capacitor. In our case, if we are talking about the chip capacitors, multi-layer chip, you can imagine this kind of a structure internally, but specially made X and Y capacitors in MLCC type have two special properties. One of them is also this internal electrode structure. So you can see here there are many internal electrodes. So you can also imagine this is a network of parallel and series capacitors. And we have many advantages from this structure. And the only disadvantage is that we can achieve less capacitance. But the main advantage is that we have more voltage rating. We have higher voltage rating like this, because we have series capacitors. And also In the event of cracking, as you can see in the image, if we could have cracking like that, we will only be into risk of shorting just one of the layers. So we have more or less redundancy, and we will not have a short circuit, which is what we always want to avoid in this kind of high voltage application. Now, another property is the coating on the external faces. This is normally applied to improve high voltage performance, avoid arcing, especially when there is some dirt or on the some environmental effects on the surface. In our case, we have a product series called Big Cap CSSA, and we have both X2 and Y2 chip MSCC capacitors, and they are all limited to 250 volt. Now, this is a limitation of the technology, and it's also related to the sizes, because in the end, we are not able to get more than 3 or 4 millimeters creepage. And now, there is one mistake here. This should be 1808 size. But yeah, we have both types of class 1 and class 2 capacitors. Of course, if you require a very stable capacitance, you need to select a class 1 capacitor, but of course, there are only very, very small capacitance values for this technology. Now, I mentioned before the standards. Why I mentioned also why we require so much safety regulation and standard. This is because this equipment is working on a high voltage, and there is a requirement for high reliability. One of the main aspects of the standard is the impulse voltage ruggedness. Now, this is the main difference between the different classes. We mentioned before X2 and Y2, but there is also X1 and Y1. And the difference between them is the level of voltage that they are supposed to pass in the impulse voltage test. Now, in this test, we can expect to see self-healing, actually, because as we know, this is an intended feature of film capacitors. And in the norm itself, they are allowing us to see this kind of curve. And this means there was a self-healing episode happening, and we are supposed to measure the capacitors 24 times with a time in between pulses. But also, we can have curves like this. This is a measurement from our recent measurement. And this is an impulse where there was no self-healing. And we can assume the capacitor is already able to handle this surge voltage or impulse. And after 3 pulses like this, we can consider the test is passed, and we can skip the 24 pulses. Now, it's very important in this test that the capacitor is still functioning for its intended use as a capacitor. So we are supposed to we are measuring the capacitor before and after the test, and we have to check that the electrical properties are still within the tolerance. Another test that sometimes is confused with this, because we also use pulses, is the active flammability test. Now, depending on the class, we also have more and less voltage, but the pulse is applied as a difference. The pulse is applied on a rated voltage AC on top of that. Now, in this test, the active flammability test, the main idea is to see if the capacitor is going to ignite or catch fire due to flashover from the impulse. Now, in this test, we are not required to do electrical measurements, but what we do is we involve or we use this fabric. It's a very thin fabric, like similar to cheesecloth, and we check that the capacitors are not catching fire, or the cloth. Now, why we call this active flammability test? Because there is also a passive flammability test. It's another requirement, now in this case also against fire hazard, where we actually apply a flame on the capacitor without electric load and check that the capacitor will not catch fire by itself. So when we stop the flame, that is applied for a time between 10 and 60 seconds. When we stop the flame, we are expected to see how the capacitor stops burning. It's self-extinguishing. Now, for this, we have specially rated materials, what we use. The epoxy filling and the case materials have to be considered for this. So what is happening inside of the capacitor? We have different, as I explained before also, we have different properties on the foil. In this case, if you have a new foil, you can see this is the edge where we have no metallization. And normally also in the other edge where we have the pin, where we connect the pin, there is normally also a slightly thicker metallization, which we call the heavy edge, which is helping the capacitor to maintain its structure and also have less ESR, less internal resistance. So as you can imagine, due to different humidity and temperature aspects, we can have a degradation or a corrosion of the foil. It can look like this. This is just a schematic or graphic idealization. And you can see here spots where we have lost metallization due to different effects. It can be electrochemical corrosion, which is mainly affected by humidity in the air that is leaking inside of the capacitor and corroding, corroding the electrode. And we also have, as I mentioned before, spots where we have self-healing. This is exaggerated. It's normally not so big. And in total, when we are losing more and more of the electrode surface, we are losing capacitance and we are increasing ESR. So some capacitors are more affected by temperature and humidity than others. This is why the capacitor in the right is still very happy in the sauna. Now, as I mentioned, the combination of high temperature, humidity, and voltage is what is accelerating the corrosion of the metallization. And one way to test this are the different damp heat steady state tests, also defined in the different standards. And the most harsh test is the so-called THB 8585, which is in these conditions, 85-degree and 85% relative humidity with applying voltage, rated voltage, and this for 1000 hours. So if we have some series that are better suited for this environment or better rugged against the impact from the environment, then we can have the so-called THB type thin capacitors. In this example of a measurement, I have put capacitors under room temperature for 1000 hours and nothing happened to them. If we just apply voltage, nothing happened to them, very slight degradation on the thin capacitors on the regular. And if we only apply the harsh environment but no voltage, we have a small degradation of capacitance on the regular types. Now, if we combine all the effects together, temperature, humidity, and voltage, we can see how it is affecting capacitors over time. This is let's say, a result of a 1000-hour test. Regular X2 film capacitors are not intended to pass this test, and as you can see, we have lost most of, maybe half of capacitance. But the THB type capacitors are, as I mentioned before, are intended to pass this type of THB test, and this is also why we call them THB types. So THB just means temperature humidity bias. For this series, in our case, we have the FTXH series of THB capacitors. We include this kind of comment in the table where we specify, yes, this capacitor is passing the THB test, and in these conditions, which are the same conditions I said. Now, just for an idea about how harsh this test is, in normal laboratory conditions, we have maybe 20 degrees and 35-degree humidity, maybe a little bit dry, like in Europe, more or less. We have about 6 grams of water in the air in 1 cubic meter. But in 85 conditions, we have almost 50 times more water in the air. So, because there is more water in the air, it can also be able to permeate the protection of the capacitor and get in contact with the winding. So now there are some real images of foils. This is a foil with yes, just some examples about what I mentioned before. This is, here you can see a bit darker, the heavy edge in a new foil. And this is like the split electrode that we can see in a Y capacitor. As I said, this is also a new foil. This is a very zoom-in image of a self-healing spot where you can see clearly the metallization is gone, and in the middle, it's not easy to see, but there is a white spot where actually also the dielectric is also gone. But this is zoomed in. Normally, it's not in the same scale as the other picture. And this is also similar to the graphic I showed you. This is where you can see corrosion and partial discharge degradation on the edge and also in the middle of the foil. This is a different foil after 85 test. So I explained how we use and how we are supposed to use X capacitors. As defined by the standard, they are to be placed between L and N, between live and neutral, line and neutral. So this is what we call across the mains, or sometimes also in parallel to the mains. And you can see this kind of comment in our datasheet. Now, we have this comment because also there is a type of application that is connecting X2 capacitors, because they are rated for mains voltage. They are connecting them in series to their converter. And this is also what we call sometimes series applications, or in series to the mains. Now, why we have this is because most of the regular X capacitors are forbidden or not recommended to be used in this style. This type of application, sometimes called capacitive power supply or transformerless power supply, is where we have the capacitor connected in series to the mains, and then there is a rectifier, and this is a very simple AC/DC converter, which is low part number, low cost. And the problem is because the capacitor is acting as an AC voltage dropper, is taking the burden of most of the mains voltage. And the problem here is in the moment where we are losing capacitance due to degradation and different self-healing, different effects, we are losing the capability to burden this voltage, and then the power supply will stop working after we drop a third time capacitance. So as I said, most of the regular X2 capacitors are not recommended to be used in this application for the reasons I mentioned, but some manufacturers include mostly in the THB type of FEM capacitors, we include sometimes an exception and approve the application. As you can see in this commentary on our datasheet of FTX FTXH THB capacitors. In some of them, not all of them, we have the approval, we give the approval for use in this kind of applications. So always check the datasheet. You will find this table in the first page. Now, just to summarize some comments and some resources, I will explain what we just learned in this presentation. So I have explained what it means, why X and Y capacitors, why we need them, and what is important about the regulation that is applying to them. I also have explained why we use these high reliability technologies. We have the ceramic MLCCs with the special structure for safety, and we know now they are limited because of their size. They are limited to low voltage and low capacitance. For film, metallized film, we know that they are susceptible to high temperature and especially high humidity environment, which can provide can suppose a problem in the long term. And now there are other resources that I will give you in the next slide. But we have applications notes. We have a lot of field application engineers which are very good designing EMC filters, power supplies connected to the mains, and also three-phase. And we have Red Expert. If you don't know Red Expert, I will show you in a few slides. And we provide lots of other products for the mains filter. And also you can always contact me or contact some of my colleagues if you have questions about these components. Now, before I finish, an overview of all the capacitors that we have in our portfolio for X and Y. So we have the regular X2 capacitors. These two series, one is providing 275 volt AC rating and the other 310. This is the only difference. These are the regular, very compact, small-sized metallized film capacitors. Now, we also have a little bit larger and of course with a different structure, different construction. We have our THB type metallized film capacitors, also with 310 AC. Now, the most recent series for us is the Y2, also in metallized film type with a voltage rating of 300 volt if we use them in Y2, but also we can use them as X1, and then we have 330 volt of rating. And also we have the safety MLCCs, also class X2 and also Y2 and X1. And as I said, 250 volt AC. When you get this, the slides in PDF, you can also click here, and I have lots of links in the presentation, so you can click and get more information. Now, I mentioned before Red Expert. This is a reminder if you don't know Red Expert. This is a online platform where you can find lots of resources for the designing. In our case, we have a dedicated module called Safety X and Y, which is including all the X and Y capacitors in our portfolio, and we are including lots of curves, especially impedance curve, as well as links to, you can find links to the datasheet, to the design files, and other curves, and also the certificates are available in Red Expert. If you don't know what Red Expert is, it's free to use, and some functionality is you need to log in to get some of the functionality, but not all of it. Now, there are also some relevant application notes. I have mentioned this application note before, the ANP015 from my colleague Andreas Nadla. He's explaining how to design a filter, a single phase line filter, giving one example of specific requirements. He's also calculating the common mode choke, the capacitance, X capacitance, Y capacitance, the varistor, the bleeding resistor, everything that is needed in the filter. The same, now in a more recent application note, is also done for a 3-phase filter. You can also click on these links when you have the PDF. There are other related application notes I mentioned before. Y2 capacitors can be used across the isolation barrier. My colleague Timur is doing a review of different products that are able to withstand and are intended to be used across the isolation barrier, including the capacitors. And also, he has a short application note explaining, giving one specific example of isolated power module, why we need the capacitance across the isolation, how we can reduce it or increase it to get some benefits into the EMI suppression. As I mentioned, there are different products. We are very strong around EMC and mains filter and power applications. So we have a huge range of common mode chokes, also 3-phase. We also have varistors and other surge protection products that can be connected to the mains. And also we have full filters, which are already encapsulated. They provide some advantage. And they are already designed to pass some specific requirements. We have different topologies, 2-stage, 1-stage, and advanced, single advanced, 1-phase, etc. So you will find this in our catalog. And with this, I have finished my presentation, and we will go to the questions.
Yeah, thank you, Jon, for your interesting presentation. Now, Frank will answer your questions. So I would say we can directly start in the Q&A session. So you can write your questions in the chat, and then Frank will answer them. So then I would say first question.
Yes.
From Henning, some capacitors are specified as X and Y. So does this mean that it will fail open? I can deduce, but can you comment more?
Yeah, thanks Henning for this question. So it depends a bit which kind of technology. So for the MLCCs, there's like X and Y rated MLCCs. They have a specialized construction inside, which is the floating design, which also means that there is like that they are used to when there's a problem that they fail as open. For the film capacitors, there's also capacitors with a Y definition and also an X rating. And here's the same thing, that they are constructed in a way that you have this kind of safety feature, that when there is a failure, that it will be as fail as an open. So you can assume that they fail as an open.
Perfect. Then next question. Is it possible to have support and the application notes list used?
Sure, yeah. When you have questions to the documents, I think there's always an email address where you can reach out or contact the author directly, and we are happy to help and discuss the topics. Sure, we provide this.
Cool. Then next question. What do you mean by cracking? Is it cracking due to external medical stress, or is it to the overcurrent voltage?
Yeah, I think it's related to the MLCCs, safety capacitors, and the cracking we showed in the picture was about mechanical cracking. So when there is like mechanical forces on the PCB, then it's like the MLCCs tends to crack. And of course, when you have soft termination, you can work against it. But we just demonstrated about what this would be a typical cracking, and it is by mechanical stress.
Okay, thanks. Then next question. It's a little bit longer. There are some capacitors that are rated for high voltages, over 2000 volt. and are used as Y capacitors. How can we tell that they are actually Y caps and not just high voltage caps? High voltage caps be used as Y caps?
It's a little tricky maybe to answer completely, but also the Y capacitors definition is that they have this impulse voltage capability and have this special internal construction that is like the safety feature that when there's a failure that they fail as an open. So what you can do is you can crack the parts open and look inside the film and to see what kind of metallization you have, and then you can distinguish between a normal one and a safety one. The normal rating for the Y caps and X capacitors is like 310 volts, 300 volt AC. And the DC rating is often in a data sheet, but it's not like a specification term for the X and Y caps. This is why it's it's not, maybe you have to reach out to us to that we can clarify this. High voltage capacitors should not be used as Y caps because, as I said, with the safety features and the impulse voltage capabilities. So it's I hope I could answer it, but if it's not clear, then please reach out to us.
Then next question. Since we lost metallization, is there any lifetime prediction for X capacitors when particular overvoltage or no number of transits are applied across it?
So it means that when you apply a number of transient on the part. So lifetime prediction for Y capacitors and X capacitors is quite hard because, as also my colleague mentioned, there's like the humidity, temperature, and applied voltage topic, which influence the lifetime. There are some approaches that really to calculate a lifetime, but we do not have it now. We have measurements of the behavior of the degradation over these factors. And also, of course, we do these tests with the overvoltage impulses. But because when you have this overvoltage and there is like a self-healing, then you lose a bit of metallization, so it's not so much. So there's normally no influence in this capacitance degradation. But of course, when it's too much overvoltage, then the capacitor can be damaged and so on. So the answer is from our side, there's no lifetime model or calculation for a lifetime prediction.
Then next question. The VRC rating is RMS, yes?
Yeah, so the voltage rating, what we have, this 310 volt is like an RMS value. And yeah.
Then next question. Does 2 X capacitance in series is equivalent to 1 Y capacitance?
This is a good question, and it depends on the standard you have to fulfill. It really depends on the requirement of the system. We can have a exchange about it, sure. So please reach out to us, and when I know more about the requirements, then we can be more have a more clear answer to this.
The next question. When we are saying even short of the X capacitors will not cause any issue to the circuit, how?
Yeah, I think even short of this will not cause any issue. I think the colleague mean that when there is like how to say, when there's a shortage of the X capacitor, then of course there's a lot of current, and when we assume that then the X capacitor is also like an open, then the application would still run. So, or of course when there's like a fuse before the X capacitors or for the overvoltage protection in the mainline filter, then maybe the fuse blow up. But I think the colleague mentioned that when there is that the X capacitors do like this filter purpose, but if the capacitor is not there, the circuit still function. I think this is what I meant. But yeah, again, when it's not something unclear, please reach out. Then we can have a more detailed discussion.
Then I would say one last question. This one. Do you provide DC voltage ratings for word safety caps? If so, how do you determine the DC voltage rating?
So yes, we in all our data sheets for the safety capacitors, we have this kind of DC voltage in the data sheet, and it's of course it's tested in the production if the film can withstand this kind of voltage ratings, and yeah, it's tested in the factory in the end.
Okay, then I would say we are finished with the session today. Thanks, Frank, for your time, for the answers. All the questions we are not answered live, so Frank or Jon will answer them via email in the next days. So thanks for joining. Hopefully we see us on our next webinar from World Electronic. Have a nice day and bye-bye.
Bye-bye.